Let us then begin our discussion with the first field bus technology part. So let's talk about then topologies, protocol stack, and benefits in this part of the discussion. So HART, it's short for Highway Addressable Remote Transmitter Protocol. So it's primarily used in SCADA applications to monitor the primary value communicated through the analog signal, which is the 4 to 20 milliamps, as well as additional digital information. So this digital information that's communicated can be an additional measurement, it can be diagnosis of the device or the status of the device. For example, let's say a mass flow meter can be able to report mass flow rate as its primary value. On top of that, it can also be able to report a secondary value, which would be something, let's say static pressure, and then it can report another third value. A tertiary value could be cumulative sum of mass that has been flowing. And so the fact that it has additional digital information, can communicate other variables on top of the primary value. In terms of the protocol stack, what happens is, as typical as it comes with field bus technologies, HART implements 3 layers, which is the physical layer, the detailing layer, and the application layer. So what we'll see as the key characteristics is that in the physical layer, it uses frequency shift key. At the detailing layer, we have a master-slave communication paradigm or type of communication, and then at the application layer, it uses 3 classes of commands. So as previously stated, HART is a master-slave communication protocol, which means the master in the network initiates communication by requesting a slave device, which is normally a field device, as data from a slave device, and then the slave device responds with the requested data. Sometimes there can be 2 masters within the single loop temporarily, mainly because then you would have a primary master connected, which would be like a PLC, and then typically would have from time to time a handheld communicator for a diagnosis or commissioning new devices connected to the same network. So the slave devices in this case become the field devices, the transmitters, the actuators, the controllers. So you'll have noticed that because it's a master-slave type of protocol, which means the master always has to initiate communication. Even if it's requesting the same type of information, it tends to request it each and every time, which is an overhead in terms of communication. So in order to speed that, what normally happens is then there will be what's called burst mode. In burst mode, the master instructs the device to continuously broadcast a standard reply. So let's say it will request it to continuously respond with the temperature. And in this case, then the master receives the data at a higher rate, which is typically 3 to 4 times per second, which is much faster than the typical mode. So in burst mode, then HART networks can be a bit faster. Since we are still at the data link layer, we said this protocol for arbitration or for choosing who uses the bus, it uses a master-slave protocol, and the HART message or a frame which are being exchanged between the devices. So this is a typical picture of a HART network. So the type of message will have this field. So it will have a delimiter, start with a delimiter, and it will have an address, which is typically 5 bytes. This will be the address of the slave. And then it will have an expansion, which is reserved for protocol extension, typically 3 bytes or none at all. And then it will have a command, which specifies the information that needs to be transferred or the action that needs to be performed by the slave. And then you'll have a byte count. This tells the application layer how long the message data is, the data that follows. And then there will be data, which is payload, the information from the slave that reports the variables that you want. So this is all the digital information, because remember the primary value the primary variable would have been communicated via an analog signal. And then it has a check byte, which is used for error checking or error detection. And this is simply an XOR of the whole message. So the device address for HART typically it's 38 bits. So if you look at the fact that the address field itself is 5 bytes, which means it can contain the whole of these 38 bits, and it's typically made up of manufacturer's ID, device type of code, and the unique ID. Sometimes the communication just uses a short address, which is typically just 1 byte. Now, at a physical layer, like we have said, it uses frequency shift keying. What it simply means is that it communicates binary information using by switching between 2 frequencies. So it will communicate 1.2 kilohertz to show that it's communicating a 1, and then to communicate at frequency 2.2 kilohertz to show that it's communicating a 0. And this digital data is superimposed, or it rides on top of the analog signal, which we carry in the primary signal, as indicated here. And then the communication requires a minimum loop impedance of 230 ohms. So still on the physical layer, so the HART network can have multiple topologies. It can be a point-to-point topology is an example of a point-to-point topology. We have a field device connected directly to a communicator. And then this would have typically need to include an impedance, because remember we said it requires a minimum impedance, and then a power supply, an external power supply, if such communication requires. Then you can see it uses a single pair of wires to connect both of these. And then sometimes you can have multi-drop communication, which means multiple devices connected on the same network. This is an example of a multi-drop communication. You have 4 field devices with 1 computer. What's interesting is that each time you have a computer, the computer needs a HART modem to connect to the HART network. So each time you have a computer and communication, you need to make sure that you have a HART modem indicated. This will appear in one of your assessments. This might appear in one of your assessments, so take note of that. And then in multi-drop, it can connect up to 15 devices. It can connect up to 15 devices. So sometimes the power supply is not needed, but at other times it's also needed. The handheld communicator, in this case, it's a configuration device. It's used for conventional commissioning of new devices, and it uses HART device description language. This ensures that it's able to communicate directly with each and every HART device. So it reads a device description file inside the HART device to understand what variables that HART device is able to measure, and what settings can be set on that particular device. So if the device has no device description file, then the HART can use the communication can simply use universal commands, which should be known by all of the devices, or common practice commands, which should be known by most of the devices. So these devices, initially stated, it can be a secondary master during the time when the network is being configured. At the application layer, so the HART uses 3 basic types of commands. So the information that's been exchanged is command. So the HART master would simply write to the slave a certain command. So that command can either be a universal type of command, a common practice type of command, or a device specific command. So universal commands are understood by all HART devices, common practice by many, but not all, and device specific are very unique. So an example of a universal command would be, say, for example, read the primary value. So each and every HART field device must understand what its primary value is and unit. It must be able to report that. A common practice command would be, on the other hand, write the device range values. So not all, but most of the devices should be able to do. And then a type of device specific command would be, say, for example, read or write certain density calibration factor. So this would only be applicable to certain devices which have something to do with density or something like that. Yeah. So some of the 2 of the 4 benefits typically obtained by implementing hard network is that it improves plant operation. The reason we say that is because you remember hard is able to have multivariable devices, that is devices that can report multiple variable information, primary, secondary, as well as tertiary information. So this redundant information can be used to verify calculations of in a plant. So this will improve the operation of a plant, and also the data from multiple devices as well, if recorded, can be used for automated record keeping, because each device will be able to record multiple variables. It also increases operational flexibility, in the sense that the hard devices, each and every one of them has device understands the device description language, which means now each and every manufacturer can write new functionalities using device description language into a hard devices, and the configuration tool will be able to understand that. And it ensures that multiple devices can also operate and talk to each other easily, because now it has the implementation of universal commands, which each and every device must be able to understand. The other advantage is that hard networks lower maintenance costs, because diagnostic information is communicated digitally into the control room, and this reduces the number of trips that are required to go into the field or hazardous areas in order to check if systems are already working properly. It also lowers cost of installation and communication, in the sense that the hard network can be commissioned in a matter of a fraction of time compared to the analog only system. And it's multi-drop, which means then on a single wire, multiple devices can be connected, and the devices are multivariable, which means instead of requiring multiple devices to measure multiple variables, then you can also use fewer of them, because each device is able to measure multiple variables. Thank you for listening to part 0. Hold on for part 1.